Good security design is not an afterthought. It is built into the foundation of every successful operation. Welcome to this session on Module 5, Physical Security, Chapter 7, Security Architecture and Engineering. In this chapter, we move beyond basic security concepts and explore how security is actually designed, planned, and integrated into physical structures. Whether it is a new facility or an existing one, security must be embedded right from the design stage to ensure effectiveness and long-term resilience. We will examine how security professionals collaborate with architects and engineers, and how design decisions directly influence the strength of protection systems. Let's begin. Security architecture and engineering form the backbone of an integrated asset protection strategy. This is not just about installing cameras or alarms, it is about designing a system where security is built into the structure itself. From the initial planning phase to construction, renovation, and expansion, security considerations must be incorporated at every stage. Security professionals work closely with architects and engineers to ensure that design choices support security objectives. This includes everything from building layout and materials to access points and surveillance coverage. The key idea here is integration. When security is considered early, it becomes more effective, less intrusive, and often more cost-efficient. Every security design project begins with understanding requirements and regulatory frameworks. Design criteria are shaped by both external and internal factors. External factors include governing codes, regulatory standards, and environmental considerations. Internal factors include organizational needs, operational requirements, and risk tolerance. A critical tool here is the risk assessment formula. Risk equals vulnerability multiplied by threat multiplied by asset value. This helps prioritize what needs protection and to what extent. Additionally, security design must comply with local, state, and national codes, as well as industry standards. Ignoring these can lead to legal issues and compromised safety. Ultimately, effective design balances compliance, functionality, and security effectiveness. Security design differs significantly between new construction projects and retrofitting existing facilities. In new construction, security can be integrated seamlessly into the design. This allows for better planning, optimized layouts, and cost-effective implementation. Systems can be built from the ground up with compatibility in mind. In contrast, retrofitting involves adding security features to an existing structure. This can be more challenging due to physical limitations, compatibility issues, and higher costs. However, retrofits are often necessary and require creative solutions to enhance security without disrupting operations. A key takeaway here is that a system is only as strong as its weakest link. Regardless of the approach, identifying and addressing vulnerabilities is essential. Perimeter security is the first line of defense, and it is guided by the principle of the 4 Ds: deter, detect, delay, and deny. Deter involves discouraging potential intruders through visible measures such as fencing, signage, and lighting. Detect focuses on identifying threats early using surveillance systems, sensors, and alarms. Delay is about slowing down an intruder, giving response teams time to act. This can include barriers, locks, and controlled access points. Deny ensures that unauthorized access is prevented altogether through strong physical and procedural controls. Additional elements like lighting and landscaping also play a vital role. Proper lighting enhances visibility, while strategic landscaping can eliminate hiding spots and improve surveillance. An effective perimeter integrates all these elements into a layered defense system. In high-risk environments, buildings must be designed to withstand blast threats and explosive impacts. Security considerations include standoff distance, which refers to the space between a potential threat and the building. Greater distance reduces the impact of explosions. Other factors include building orientation, structural reinforcement, and the use of blast-resistant materials. Design features such as controlled access points, protective barriers, and strategic layout planning can significantly reduce vulnerability. The goal is not just to prevent attacks, but to minimize damage and protect lives if an incident occurs. Effective blast-resistant design requires coordination between security experts, engineers, and architects to ensure both safety and functionality. The structural design of a facility plays a critical role in overall security. Building materials, if not properly selected, can become vulnerabilities rather than strengths. Progressive collapse is a key concern, where failure in one part of a structure can trigger a chain reaction affecting the entire building. This is why adherence to established building standards and codes is essential. Glazing, or the use of glass in buildings, presents another important consideration. Glass can act as both a functional and aesthetic feature, but it is also a potential hazard during explosions or forced entry attempts. Laminated glass, window films, and controlled placement can significantly reduce risks from fragmentation. Interior layout is equally important. High-security areas should be located away from public access zones, and critical operations should not be easily visible or accessible. Thoughtful placement of offices, control rooms, and access pathways can greatly enhance both safety and operational efficiency. In essence, security must be built into both the exterior and interior design of a facility. Utilities are the lifelines of any facility, and their security is vital for uninterrupted operations. HVAC systems, heating, ventilation, and air conditioning must be carefully designed and secured. Improperly protected HVAC systems can be exploited for contamination or disruption. Secure placement of air intakes and controlled access to system components are critical. Emergency power systems ensure continuity during outages. Backup generators and uninterruptible power supplies must be reliable, well-maintained, and protected from both physical and cyber threats. Speaking of cyber risks, modern utility systems are increasingly integrated with digital control systems like SCADA. This creates new vulnerabilities that must be addressed through proper cybersecurity measures. Ultimately, protecting utilities means protecting the core functionality and resilience of the entire facility. Life safety systems are designed to protect people during emergencies, making them one of the most critical aspects of security design. These systems include fire detection and suppression, alarm systems, emergency lighting, and clear exit pathways. They must comply with recognized standards such as life safety and building codes. Evacuation planning ensures that occupants can exit the facility quickly and safely. This requires clearly marked exits, unobstructed routes, and regular drills to ensure preparedness. In some scenarios, evacuation may not be the safest option. This is where shelter-in-place strategies come into play. These involve securing occupants within the facility in protected areas until the threat passes. The key is to assess the situation and apply the appropriate response strategy, always prioritizing human safety above all else. Effective security is never dependent on a single measure. It is built through a layered approach. This begins with understanding risk, identifying threats, vulnerabilities, and potential impacts before selecting appropriate controls. The concept of the **4DS, deter, detect, delay, and deny, *** must be applied across all layers, from perimeter to interior spaces. Integration is essential. Security architecture, engineering, and life safety systems must work together seamlessly to create a cohesive and effective protection strategy. It is also important to recognize that while risk can never be completely eliminated, it can be significantly reduced through thoughtful design and continuous improvement. Strong security is not about building walls, it's about building systems that think, adapt, and protect. Thank you for joining this session on security architecture and engineering. I hope this has given you a clear understanding of how layered, integrated security design works in real-world scenarios. Thank you, and wishing you success in your CPP journey.